grass. Picture to yourself that it has been a very hot summer's day, and the ground and the grass have been well warmed, and that the sun goes down in a clear sky without any clouds. At once the heat waves which have been stored up in the ground bound back into the air, and here some are greedily absorbed by the vapor, while others make their way slowly upwards. The grass especially gives out these heat waves very quickly, because the blades, being very thin, are almost all surface. In consequence of this, they part with their heat more quickly than they can draw it up from the ground, and become cold. Now, the air lying just above the grass is full of invisible vapor, and the cold of the blades, as it touches them, chills the water particles, and they are no longer able to hold apart, but are drawn together into drops on the surface of the leaves. We can easily make artificial dew for ourselves. I have here a bottle of ice, which has been kept outside the window. When I bring it into the warm room, a mist forms rapidly outside the bottle. This mist is composed of water drops, drawn out of the air of the room, because the cold glass chilled the air all round it, so that it gave up its invisible water to form dewdrops. Just in this same way, the cold blades of grass chill the air lying above them, and steal its vapor. But try the experiment, some night when a heavy dew is expected, of spreading a thin piece of muslin over some part of the grass, supporting it at four corners with pieces of stick, so that it forms an awning. Though there may be plenty of dew on the grass all round, yet under this awning you will find scarcely any. The reason of this is that the muslin checks the heat waves as they rise from the grass, and so the grass blades are not chilled enough to draw together the water drops on their surface. If you walk out early in the summer mornings and look at the fine cobwebs flung across the hedges, you will see plenty of drops on the cobwebs themselves, sparkling like diamonds, but underneath on the leaves there will be none, for even the delicate cobweb has been strong enough to shut in the heat waves and keep the leaves warm. Again, if you walk off the grass onto the gravel path, you will find no dew there. Why is this? Because the stones of the gravel can draw up heat from the earth below as fast as they give it out, and so they are never cold enough to chill the air which touches them. On a cloudy night also you will often find little or no dew even on the grass. The reason of this is that the clouds give back heat to the earth, and so the grass does not become chilled enough to draw the water drops together on its surface. But after a hot, dry day, when the plants are thirsty and there is little hope of rain to refresh them, then they are able in the evening to draw the little drops from the air and drink them in before the rising sun comes again to carry them away. But our raindrop undergoes other changes more strange than these. Till now we have been imagining it to travel only where the temperature is moderate enough for it to remain in a liquid state as water. But suppose that when it is drawn up into the air, it meets with such a cold blast as to bring it to the freezing point. If it falls into this blast when it is already a drop, then it will freeze into a hailstone, and often on a hot summer's day we may have a severe hailstorm, because the raindrops have crossed a bitterly cold wind as they were falling, and have been frozen into round drops of ice. But if the water vapor reaches the freezing air while it is still an invisible gas, and before it has been drawn into a drop, then its history is very different. The ordinary force of cohesion has then no power over the particles to make them into watery globes, but its place is taken by the very process of crystallization, and they are formed into beautiful white flakes, to fall in a snow shower. I want you to picture this process to yourselves, for if once you can take an interest in the wonderful power of nature to build up crystals, you will be astonished how often you will meet with instances of it, and what pleasure it will add to your life. The particles of nearly all substances, when left free and not hurried, can build themselves into crystal forms. If you melt salt in water and then let all the water evaporate slowly, you will get salt crystals, beautiful cubes of transparent salt, all built on the same pattern. The same is true of sugar, and if you will look at the spikes of an ordinary stick of sugar candy, you will see the kind of crystals which sugar forms. You may even pick out such shapes as these from the common crystallized brown sugar in the sugar basin, or see them with a magnifying glass on a lump of white sugar. But it is not only easily melted substances such as sugar and salt which form crystals. The beautiful stalactite grottos are all made of crystals of lime. Diamonds are crystals of carbon, made inside the earth. Rock crystals, which you know probably under the name of Irish diamonds, are crystallized quartz, and so with slightly different colorings are agates, opals, jasper, onyx, cairngorms, and many other precious stones. Iron, copper, gold, and sulfur, when melted and cooled slowly, build themselves into crystals, each of their own peculiar form. And we see that here is a wonderful order, such as we should never have dreamed of if we had not proved it. If you possess a microscope, you may watch the growth of crystals yourself by melting some common powdered niter in a little water till you find that no more will melt into it. Then put a few drops of this water on a warm glass slide and place it under the microscope. As the drops dry, you will see the long transparent needles of niter forming on the glass, and notice how regularly these crystals grow, not by taking food inside like a living being, but by adding particle to particle on the outside evenly and regularly. Can we form any idea why the crystals build themselves up so systematically? Dr. Tyndall says we can, and I hope by the help of these small bar magnets to show you how he explains it. These little pieces of steel, which I hope you can see lying on this white cardboard, have been rubbed along a magnet until they have become magnets themselves, and I can attract and lift up a needle with any one of them. But if I try to lift one bar with another, I can only do it by bringing certain ends together. I have tied a piece of red cotton round one end of each of the magnets, and if I bring the two red ends together, they will not cling together but roll apart. If, on the contrary, I put a red end against an end where there is no cotton, then the two bars cling together. This is because every magnet has two poles or points which are exactly opposite in character, and to distinguish them, one is called the positive pole and the other the negative pole. Now, when I bring two red ends, that is, two positive poles together, they drive each other away. See, the magnet I am not holding runs away from the other. But if I bring a red end and a black end, that is, a positive and a negative end together, then they are attracted and cling. I will make a triangle in which a black end and a red end always come together, and you can see the triangle holds together. But now if I take off the lower bar and turn it so that the two red ends and the two black ends come together,